So, good morning, everybody. Myself, Acharya Vishwendran. Today, I shall be discussing a worksheet on logic gates itself. So, let's begin with things. So, here is the worksheet on logic gates, especially for all the gates together. So, first is we have to draw the logic symbol of NOT gate. So, NOT gate is like this, and its Boolean expression is y is equal to x bar. Y is the output here, and x is the input. Similarly, for OR gate, we have two inputs and one output. Generally there can be more than two, but at least two inputs are required, and its Boolean expression is x plus y. Then we have AND gate, so it is like this, and Boolean expression is x dot y. Then we have NOR gate, and it is like this, and the Boolean expression is x plus y bar, or using De Morgan's law it can be written as x bar dot y bar. Then we have NAND gate, which is x dot y bar, which is x bar plus y bar, and it is represented as this. Next we have exclusive or XOR gate. XOR gate has the truth table as x plus y like this, and it is equivalent to x bar dot y plus x dot y bar. Next is we have XNOR gate. So if we just add a NOT gate to XOR, we get XNOR gate, and it has the Boolean expression like this, which is equivalent to this. Next is the truth tables. So first is for NOT gate. So we have x as 0 and y as 1, or x as 1 or y as 0. That means corresponding to low input there is a high output from NOT gate, and corresponding to high input there is low input, which is the physical significance of this truth table. Similarly, for OR gate, we have high output if at least one of the input is 1, which is given by this truth table. Then for AND gate, we have high output only if both inputs are 1, otherwise it is 0. So this is a truth table for AND gate. Next is NOR gate. So NOR is just inverter of the OR gate, or if you add NOT gate to OR gate, you get a NOR gate. And the truth table is 1000. That is, it gives a high output when both the inputs are low, otherwise it gives the low output, which is the logical explanation for this. Then we have NAND gate. So NAND gate is again obtained by adding NOT gate to AND gate, and its truth table is 1110. That means it gives low output only when both inputs are high, otherwise it gives a high output. Then we have XOR gate. So in XOR gate we have low output when inputs are same, and high output when inputs are different. And XNOR is just invert this thing. So in XNOR gate, output is high when inputs are same, and output is low when inputs are different. So that is the logical explanation for this. Next is circuit diagrams for realizing this. So for NOT gate, we can use a transistor for that. A transistor in saturation and cutoff state acts as NOR gate. Corresponding to low input, it gives high output, and corresponding to high input, it gives low output. So it is just a transistor. You can take the output as X. Then we have OR gate. OR gate can be realized by using two diodes. So take two diodes D1 and D2, make a load over here, and take this point as Z and earth this. So the output will correspond to the OR gate, and it can be verified using the truth table. Next is for AND gate, we can use invert the diodes, and it follows the same logical expression and the same truth table as that of AND gate. Next is NOR gate. So for NOT, you just add OR gate to the NOT gate. So it's the combination is equivalent to NOR gate. Then for NAND gate, we can use AND plus the transistor, which gives the NAND gate. Then we have XOR gate. So XOR gate can be realized using a combination of NAND or NOR gates like this. So it gives the same output as that of the XOR gate, which we have already read, which is corresponded by this truth table. So in this way, I just tried my best to optimize your time and energy so that you can cover the entire topic within a few minutes, and can end up with flying colors. Thank you and have a nice day.